All right, so last day dealing with LU Decomposition. You don't want to consider right now. All right, so where we're at right now is if we're not needing for row interchanges, we have point A equal to B, the LU Decomposition, solve lower triangular system by forward substitution, upper triangular system by back substitution, and then we're done. But generally does not go that way. You need to perform row interchanges for one reason or another, not just to avoid dividing by zero in competing multipliers, but also to contain the propagation of round-off error. I mentioned a couple of pivoting strategies last time. Partial pivoting and complete pivoting. Now, what I'm going to talk about today is what does the LU decomposition look like when we're taking pivoting into account? How do we come up with it in that case? So if we're mixing, because way is now A equals LU, the only thing we're doing during elimination is we're subtracting a multiple of one row from another, only using that one type of row operation. And in that case, remember from last time, or two classes ago, this is what we ended up with. We started with matrix A, and then multiplying A on the left by unit lower triangular matrices to get your row echelon form, your U. And to refresh your memory, each one of these M's here has a job of eliminating all the entries in a particular column. So this works in the first column, this works in the second, all the way to column n-1. The inverse of this product ends up being L in this case. But now, before we work on a column, we might have to do a row interchange. And that leads to this sequence of operations applied to A to get U. So first, you multiply A on the left by what's called a permutation matrix. I showed you these last time. A permutation matrix is where you are scrambling the rows of identity. That's how you actually get the matrix. So this matrix P1 is its job is to swap row 1 with some other row down below to make sure that the diagonal entry in column 1 is as large as possible. Okay, now if we're using partial pivoting. Now, I'm not really assuming any particular pivoting scheme, just one that only performs row interchanges. So what I'm showing you here rules out complete pivoting because complete pivoting swaps both rows and columns. So here we're just dealing with rows. Okay, so once you performed a row interchange, if necessary, to get the proper entry in the 1-1 position, now you go ahead and eliminate the entries in column 1 below the diagonal. Okay. Then you move on to the second column. You possibly perform a row interchange again to swap row 2 of some other row, and you work on column 2, and it keeps going. So now you have P, M, P, M, P, M. So permutation matrix, elimination, permutation elimination until you're finished. Okay. Now it's possible that any of these permutation matrices could be identity. In a situation where it was not necessary to perform a row interchange. But for now, we'll assume that it might always be necessary. So we have these P's thrown in between the M's. Now, the way I define L at the beginning of the section is it's a product of the inverses of all of these M's. Now, the problem here is, matrix multiplication is not commutative. I can't just take all these P's that are in between these M's, I can't just shuffle them all the way down to the end. I can't change the order of these, so it would be incorrect. So we need to perform some trickery here with matrix multiplication in order to figure out how do we get a matrix L out of all of this, because we're still trying to get an LU decomposition. It's just not clear how we can the way this is written now. So here's what I do. So before I have P1, M1, then P2, and then everything else. So everything from this P2 to the left is not going to change. And then I have P1A, that part isn't changing either. But what I do is I put in a P2 inverse P2. So M1 has a P2 on the left, on its left. So I'm going to put a P2 inverse on its right. But if I'm going to introduce that, then I have to put a P2 next to it. All right. Now, so this equation here is equivalent to this one. But notice it's allowed me to put P2 right after P1. Because I would like to take all permutation matrices and move them down to be directly in front of A. I just don't know how to figure out how to do that and what am I going to be left with. Now, I need to give a little fact about permutation matrices. Permutation matrix has a property that is an orthogonal matrix. And what we know about an orthogonal matrix is that the P transpose times P is identity. So it means that, it's an unfortunate terminology, when you have an orthogonal matrix, it means that the rows and the columns of the matrix are orthonormal. Like if you take a dot product of any two rows or any two columns of an orthogonal matrix, you'll get 1 if it's the same row or column, or 0 otherwise. So the rows form an orthonormal set, so do the columns. Another way of looking at it is that the inverse of the orthogonal matrix is equal to the transpose. All right. So this P2 inverse here, I can write it as P2 transpose. So that's simplified better. You don't have to actually try to compute an inverse. And then what I do is, right now I have P2 M1, P2 inverse, or P2 transpose now. So I can define that to be M1 tilde. Now, M1 is a matrix that carries out elimination. It subtracts from multiple one over another. It's a unit lower triangular matrix. Now, it's not pretty obvious what I'm showing here, but what I've shown you so far. But this matrix, you multiply by P2 on the left, P2 transpose on the right. The resulting matrix, M1 tilde, is also unit lower triangular. Okay. For a lot of y'all, so I need questions up to this point. Yes.
That line that now we be working. So there, all the matrices, they have the same dimension.
Yeah, all these are square n by n matrices.
Okay, and then when we multiply, what will be the problem if we change the position? Like you said that P1A should be there, and the order should be that order.
Well, really what I want is, I want to have all the m's together. Because because of this. Because if the ends are unilower triangular, so then I can take a product over inverses, I can call that L, the LU decomposition. But and the thing is, because of the non-commutativity of matrix multiplication, I can't just shuffle them around. But at least with this trickery, I can get there. Okay, so after doing all that, this is where we stand now. So at least P2 and P1 are together, and now I have M1 tilde and then the original M2 are together. But now I have all these other simplification matrices further down the line that I'd also like to have moved over here. But what I can do is I can use the same idea as before. Like I can take I can introduce a P3 transpose P3 right here because P3 is orthogonal, so P3 transpose P3 is identity. And then what I can do is, so now all P1, P2, P3 are all together. And then I also put a P3 transpose P3 here in between M1 tilde and M2. So now I have this, so M1 is being modified yet again. And then I have a modified M2. So I can just continue this process where I keep moving permutation matrices to the right. Permutation matrices themselves don't change. The M's do get modified because they're always being multiplied on the left by permutation matrix, on the right by its transpose. So those do not come out unscathed, but at least they're in the right place now. So eventually I get to this point where I have all the M's but modified, and then I have all the permutation matrices, the original permutation matrices, times A is equal to U. And the way I can define all of these modified M's, the M tildes, is with this formula right here. So I start with the original M superscript J, and I multiply on the left by permutation matrices and on the right by my transposes, but only for indices greater than J. By only using ones with index greater than J, I'm guaranteeing that the modified matrix is also unit lower triangle. Now, the sort of thing that's difficult to see unless you actually play the matrices and actually, I think I have a MATLAB diagram for you later. I have an example about this, but no. Apparently I don't. Okay. Let's check something in the text. Oh, yeah, I do have an example. Okay. So that's an example. Here's like my original M1 that's meant to work on column 1, but it has these multipliers, or actually they're negated multipliers in the first column. So what happens is the modified M1 is I have a permutation matrix, I'm calling here P2, and P2 in this case swaps rows 2 and 3. So this is what P2 looks like. So if I take M1, this M1, and I multiply on the left by P2, so I swap the second and third rows, that will wreck the unit lower triangular structure. But then I multiply on the right by P2 transpose, which is going to, on the right, that's going to swap the second and third columns, and that will restore the unit lower triangle structure. So this is a modified P1. And the only difference between the original and the modified is that the multipliers in rows 2 and 3 have been switched. So the effect is, when you are performing a row interchange, that's going to have the effect of swapping multipliers. But only those, yes.
This can be a silly question, but I was trying to understand exactly what P1 is.
Okay, so any P's, their job is to interchange rows. Now, in this particular example, with the Gauss elimination with partial pivoting, so what happens is, okay. Oh. Oh, so this is a situation that it's actually not really fully implementing partial pivoting, but what it's doing is it's only carrying out row interchanges when absolutely necessary. Like in this case, partial pivoting would have called for swapping row 3 and row 1. But we just don't do that here because it's not really necessary. So we finish column 1. Then when we get to column 2, we have a 0 here. We must interchange rows. So that's why we swap rows 2 and 3. And because we're doing it before we work on the second column, that's why it's called P2. Swap rows 2 and 3. Yeah, so P1 in this case would be identity, because we never did a row interchange yet.
And then P0 is not switching it. I see.
Yeah. Are you question?
I wanted to ask, why is the multiply in the lower triangular matrix negated?
Oh, because you're subtracting multiple of row J from row I. Now, but that's in the M, so then you invert those to get L, which removes the minus. Okay. So, if I do what I did before, I wasn't pivoting. Like all of these matrices are unit lower triangular. They contain multipliers in the appropriate column. And if I invert the product of all of these, that would be L. But what I've done effectively is compute the LU decomposition not of A, but of a row interchange version of A. So this matrix is A with all the row interchanges performed up front, like as if we knew what they were going to be when really we don't. So A itself does not necessarily have an LU decomposition, but this row interchange version of A does. So instead of computing A equals LU, we have PA equals LU, where P, and I should clearly state the definition of P. P is just a product of all these permutation matrices in order. Okay. Otherwise, the other decomposition is what we've seen before, that L contains all the multipliers in the lower triangle. U is a result of, it's a row echelon form that you get by elimination on the row interchange version of A. Now this is rather messy to try to come up with this LU decomposition when you're doing pivoting. But what about the Gauss elimination algorithm? How does pivoting affect that? And it turns out that it's actually easier to come up with the correct L in code. You don't have to do all this that I showed you here, because in effect it's being done for you. So you want to make sure that you're computing this correctly when you're carrying out row interchanges before you work on each column. here's what you do. So this part you're doing anyway. The multiplier that you get to eliminate the entry ij, you're storing it in the ij position. So that happens with or without pivoting. And then here's the key step right here. When you decide that you need to interchange like row J and row P, what you do in your code is you apply that interchange to the entire row. Now, in elimination, the first portion of that row is 0, to the left of column J. But you're not leaving it 0, you're stuffing multipliers in there. So as you swap rows of a matrix you're working on, that you're actually applying eliminate row operations to, you also are applying a row interchange to the stored multipliers. So in code, as long as you do this, swap the entire row J and whatever row P you're interchanging with, then your multipliers will end up in the correct place. So it's actually quite easy to basically implicitly carry out all this so that you have this decomposition carried out correctly. There's an exploration in section 3.2, it's 3.2.20, where you implement partial pivoting. And you also make sure to do this when implementing it. There are a lot of hints given on that exploration. It's definitely the hardest one assigned so far. And you'll want to take a close look at those. Okay. So how this works now is gas elimination with lower pivoting scheme. It's called interchanging rows. You're creating LU decomposition of PA rather than A. And so we're carrying out gas elimination with row interchanges and then doing this, you'll get this decomposition. But the thing is, AX equals B now becomes PAX equals PB. So pivoting is taken into account here. Whatever row interchanges you apply to A, you also have to apply to B before you carry out forward substitution. So don't forget to do that. And then the last step is on change. You solve UX equals Y by back substitution to get the actual solution. Row changes have already been taken into account, so there's no need to do anything more with them there. From a storage point of view, P is a permutation matrix, but it's a matrix that most entries 0. It's just ones at various places, like from shuffling rows of identity. You should not store it explicitly. That's very wasteful. What's more efficient is if you start with a vector of indices, like a row vector, one that has row indices 1 through n, so originally they're in order. Whenever you swap rows of A, you swap the corresponding indices of this vector. And then you can use the indices in that vector to rearrange the elements of B. Instead of multiplying B by an actual permutation matrix. Now MATLAB makes it very easy to do. So P is a vector of indices that have been scrambled. If you do this, B parentheses P, this expression will be the elements of vector B in the order you want, according to the indices stored in P. So that's really all you have to do. So questions about the LU process when we're doing pivoting. Okay, straight to things in MATLAB, but it will help you understand what's going on here. Okay. first we're gonna create this random matrix. I think we're missing something. Okay. Oh, you know what? I think I'm missing a page of this diary. Hold on. Hoping that, no, it printed out yesterday, hopefully someone else. Yep, I found it. Okay. So I actually did want to do this, but I won't leave it later. Okay. I'm gonna make an example, M1, again, the kind of unit lower triangular matrix. It has negative multipliers in the first column. So what I'll do, a unit lower triangular matrix has ones on the diagonal, like the identity matrix does. So first, I'm going to start by making an identity matrix. And then I'm going to put, since it's an M1, it works in the first column, I'm going to stuff random numbers in here. So, so in column 1, but entries 2 to the, 2 down to the last. I'm going to take random numbers. There are 4 entries here, so I need a random column vector of length 4. Now, rand gives you random numbers between 0 and 1, uniformly distributed. I'm going to put them between -1 and 1, just have a mix of positive and negative. All right, so here we have random negated multipliers put here. Now, I'm going to assume that there's pivoting going on. Let's suppose that when working on column 2, I needed to swap row 2 with row 5. So let's assume that the entries just happen to work out that way. Now keep in mind that during Gaussian elimination, the matrix P sub j swaps row j with some row I that is greater than j. So it always works out that way. So what I'm going to do is I'm going to create a permutation matrix that does this. It'll swap rows 2 and 5. So first I'll create identity. And then I'm going to overwrite P rows 2 and row 5 with those rows in reverse order. And I showed you something like this in another previous class. So I have, what I'm doing on the right side of equals is I'm extracting row 5 followed by row 2. So I have indices 5 and 2, all columns. And then I assign those to the submatrix consisting of rows 2 then 5. So because I have 2, 5 here and 5, 2 here, that has the effect of swapping rows 2 and 5. So there we have that. Now what I'm going to do is I'm going to multiply my F1 on the left by P2. Now, that'll put the multipliers in the right order within column 1. But now my unit lower triangular structure is messed up because row 2 and row 5 got swapped the entire rows. So this is in the wrong place and this is in the wrong place. So then what I'm going to do is override this with itself times P2 transpose. I'm going to swap columns 2 and 5. And then unit lower triangular structure is restored. Now, there's something very important I want to point out so you can understand why this works out well. Because you gotta be careful playing your permutation matrix. Look at the way I define each M tilde. I take MJ and I apply permutation matrices to it, but only with greater indices than J. That's essential. And now I can explain why it works that way on this example. Because, all right, I'm swapping rows 2 and 5 first. Okay, so this 1 is not going to be disturbed because I'm not touching row 1, only later rows. And yeah, okay, well, these 1s are now scrambled. But because this permutation matrix swaps rows of higher indices, my multipliers are in column 1. This is swapping columns 2 and 5. This column, I can guarantee, will not be touched. So multiplying on the left, got the multipliers in the correct order, multiplying by the transpose on the right will not undo that work. That's the key. So the only purpose that multiplying by P2 transpose on the right does is getting all these 1s that are to the right of these multipliers back in place. But this only works because I'm applying permutation matrices with indices greater than the column where these multipliers are housed. Note that here. This works because multipliers are in column 1, but columns 2 and 5 are swapped. The validity is greater than 1. It will always be that way. So in general, MJ is acted on by PK and PK transpose for K, and what I emphasize is greater than J. And that's why that lower triangular structure is always preserved. Okay, so questions about any of this? So, your amusements, I'm going to confess to something embarrassing. I've taught this type of class a great many times. Well, actually, yeah, almost every even numbered year, spring, since I've been here, dating all the way back to 2010. There was one time when I got assigned last minute stuck in a shoot, but otherwise, every single time. That's a lot of times. But not only that, I also taught it a few times at the similar class at Stanford, also once at UC Irvine. So a zillion times. Now, a long time ago, I had actually told my class that when we had this situation here of these alternating permutation matrices with these M's, and I wanted all the permutation matrices over to the right, I actually told them and somehow proved that I could just take these P's and move them down to the right, and it would and not touch these M's, and it would work. And they bought it. And at some point, I was about to re-examine this, right? Like, oh wow, I was playing wrong all this time. And I don't remember exactly when I fixed it. It was several years ago. But at least now you all are getting the correct story. And that's what made it into a book like this. The funny thing is, this sort of aspect of LU decomposition, I mean, every book covers it. Every such book is going to cover LU decomposition with pivoting and how your PA equals LU. But as far as playing with the P's and the M's, no one touches it. Yeah. What?
This looks ugly.
Well, yes, it does. Yeah. But I just had to know. It's like, how do you get PA equals LU? How do you get those P's over there? Why does this work? I'm like, oh, okay. Yeah. But yes, no one cares about it. Or I guess you don't want to write about it. Now, now what I'm gonna do is I'm gonna show you what using what happens to use MATLAB's own built-in LU function. So I have this random matrix A that I mistakenly created earlier, but now I actually want. And I'm going to show you how MATLAB's LU function proceeds. So you specify three outputs, L, U, and P equals LU of A. So if I go ahead and do that, then sure enough, we have this unit lower triangular matrix L with all the multipliers that were used. We have a upper triangular matrix U, and then we have the permutation matrix P as a full matrix. Although it occurred to me, I bet I haven't done this, but I bet if I were to look at the help page for LU, it probably has a way to return P as a vector rather than this full matrix that's wasting storage, because that's certainly what would make sense. Okay. So here's all the different ways you can call LU. Ah, yes. I can specify a second argument that's either a word matrix or a word vector in quotes, and it will give, if I just say vector, by default the matrix like I just showed you, but if I say vector here, P will be a vector that's more efficient for actually applying these row interchanges. So if I do that, I'll call it something else, P vec, LUA vector. And it's going to give me the same L and U as before. But now, here are the indices in the correct order after all row interchanges have been applied. Okay. All right. Oh, when I did this diagram 2 years ago, I just made this vector manually instead of LU give it to me. But it's certainly important that everyone's aware of this too. Okay. So now we have P described as a matrix and as a vector. So now what I'm going to do is I'm going to apply this permutation to A. So I do P vec, so I'm scrambling the rows to put them in this order, and then specify all columns. So I'm going to bring A back. Here's A, and then I do A with the rows rearranged. So, for example, here's row 4 of the original A, but now it's in row 1 because that's the first element of P vec. Here we have row 3, the original A, that's now in row 2, it's 3 to the second position, and so on. So this is the row scramble version of A. Okay. Now, the other way I can compute it is if I take the matrix P that I generated earlier and multiply that by A, and that will have the same effect. Right. So these are equivalent. Row indices rearranges rows. Okay. So now what I'm going to do is I'm going to use MATLAB LU again, but not on A. I'm going to use it on the row interchange version of it that I obtained earlier. Okay. So what this does is swap rows first, then do the LU decomposition. Okay. Now let's see what happens. So we get L, we get U, and notice that P is identity this time, because whatever row interchanges the Gauss elimination of partial pivoting would have done on the original A, those four interchanges have already been applied to the matrix that I said to LU this time. So then the estimation partial fitting algorithm decides, oh, the correct entries in the diagonal position each time, there's no need to interchange the rows, so P just becomes identical. The last thing I'll do in this diary, so for exploration 20, what's necessary to do is swap rows of the matrix, but also swap elements of the vector. Rows in matrices versus swapping indices in the vector. And I've shown this before for matrix. Like if I take rows 2 and 5, and we'll swap them. Okay, so we've seen that before. Now, if I have the vector, like P goes from 1 to 5, so the P is a row vector 1, 2, 3, 4, 5. If I do this, so P is a vector though, so I don't have a comma colon. Otherwise, it's exactly the same. So this is swapping elements 2 and 5 of this vector. It doesn't matter whether it's row or column vector; it's going to have the same effect. So those are kind of operations that you would do in that exploration to implement partial pivoting. But you have variable indices instead of constants like right. The questions about what happens in this diary. Okay. Okay. Now, I mentioned earlier, if you have the LU decomposition, how it's easy to do determinants, and I'm going to revisit that topic in case where we have pivoting involved. Now, if PA equals LU, then I can say that A is equal to P inverse LU. That's the same as P transpose because it's orthogonal. So the determinant of A, we would determinant of this product as A is equal to this product. But remember, determinant of a product is the product of determinants. So we have the determinants of these matrices individually. But determinant of the matrix is the same as the determinant of its transpose, so really we just have determinant of P itself. L is a unit lower triangular matrix, so it's determinant of 1. U is upper triangular matrix, so this determinant of the product follows diagonal entries. So now we have this. So this is formula we had before. We weren't pivoting at all for the determinant. So now we just have to remember to multiply that by the determinant of P. Now, what is the determinant of P? And P is an orthogonal matrix, so we have P transpose P's identity. So, so I can apply that here, and using also properties of determinant, like transpose doesn't change it. I get determinant of P squared. So that tells me that the determinant of P is equal to plus or minus 1. So multiplying all the diagonal entries of U now does not necessarily give us a determinant, but at least gives it tells us what the absolute value of the determinant is. Now, how do you know if it's plus or minus 1 without like going through total computing it? here we use a property that whenever you swap two rows of the matrix, that changes the sign of a determinant. So if you start with P initially representing the identity matrix, and you're carrying out Gauss elimination of pivoting, every time you perform a row interchange, that's going to negate the determinant. So we can say this: the determinant phase equals to -1 to the S power, where S is how many row interchanges you actually performed during Gauss elimination of pivoting, and then you multiply that by all of the diagonal entries of U. So it's still quite easy to compute the determinants using LU decomposition, even when pivoting is involved. You just have to remember to account for this. It's still certainly preferable to computing the determinant using formula to learn for it in a linear algebra class that would take n factorial operations. Okay. All right, so we've come to the end of this section at last. Okay. So any questions about what we have here?
Not yet.
Okay. That's for one. All right. Okay, let's look at the homework for this section. Okay, 4, 5, 9, 10. And as you see here, there's a hint file. Definitely look at that. But I'm going to go through and if anything jumps out at me that I should mention. Okay. Of course, yes, this one's a pain that we have proofs to carry out. Although, and once you prove that the product two upper triangular matrices is upper triangular, it's not so interesting to the lower triangular case. So I won't be too concerned about that. And then, yeah, for this one, you want to take into account, if you're computing the inverse one column at a time, you're solving a system of equations where the matrix of the system is either lower or upper triangular. And again, you'd have to pick one kind of triangularity and work with that. And so, for instance, if it's lower triangular, you're using forward substitution. And the right-hand side is the column of identity. So how's forward substitution going to proceed in the case? It might be a good idea to work with a small example when you can see what's going on. Okay. This one is relatively quick. There may be a way to answer in class. Yeah, I think we did. Nine. Okay, yeah, it's went forward substitution based on the algorithm. Be sure to test it. Okay, yeah. LU decomposition, be sure you follow the actual algorithm. And it'd be a good idea, like, are you supposed to do this by hand? MATLAB can be helpful in terms of checking your answer. Actually, one thing I should mention is, okay, if I do integrated matrix, Hilbert matrix, which has all fractions for its entries, and here we see them as decimal stuff. But if you do format rat and display H again, now you can see the fractions. The fraction's only an approximation, but in this case, you're dead on. So when you're carrying out LU decomposition by hand, I better put this back. I'm going to forget that. Why don't we fraction? You're going to get fractions because since the entries initially are integers. So if you want to like take the matrices L and U that you get and multiply them in MATLAB, then I should mention do not want to check your work here by actually calling the LU function, because LU is going to perform partial pivoting, which you're not doing here, so the result will not agree in that case. You're wasting your time. Okay. All right. Okay, modifying Gaussian from the last assignment to return one matrix that has multipliers, lower triangle, and then row echelon form of the other triangle. Notice there's no B anymore, so you're gonna remove that part. Okay. Okay, now we're getting pivoting. Okay, Gauss elimination with partial pivoting on this matrix. So something interesting could happen, otherwise it's up. Okay. Oh, and then complete pivoting. So something different should happen. Okay, and then the last one, I'll take more time than all yours combined, is oh no, proof into the positive. Is this one. Now here's the first example we've seen all semester of a function that we call other function, because by this time, trying to get this far from between this homework and the previous one, you already have a function for Gauss elimination. You already have one for forward substitution. You already have one for back substitution. So solve HB by itself should do very little. It should just call those functions. But the Gauss elimination one has to be modified. That's the main part of this problem. That it's not solve HB, that part's quick. But modify your Gauss elimination function to account for partial pivoting, and also return not just LU, like returning the same LU in one matrix that is the previous problem, one of the previous problems, and then also return P, the vector of scrambled indices that you can use to account for a partial pivoting. Okay, but again, look at the hints file. It wasn't a hints file for homework 1, but I go on and on about problem 20. So, and problem 4. So everything between is I think this typo was already fixed. Okay, so that's your warnings for homework 2. Alrighty, so yeah. Yeah. Okay. Stop recording.